Hi, everybody. Here we are again. Every year it gets a little more interesting. Kind of like I was saying to Larry, it's like the Great Walendas. We're walking on this pretty high wire, and I think the wire is a little bit higher this year than it was last year. The CTO Challenge guys have a lot on their plate, which we'll see this afternoon. And I think probably all of you or most of you were with us last night, so I won't repeat that speech. But I do think I'll use one term that I used the night before, and that is, it seems as though at a time when we're experiencing logarithmic growth in change of every type, that systems level thinking is the right answer. And this thing which Larry invented, this idea of, Larry Smart, this idea of century scale changes, we should be looking at them more carefully because they are the big things. They do carry with them thousands of other technologies and companies and the fate of nations and so forth. So we want to look at those things, and we will look at them this week. But I think throughout today and throughout the week, we're trying to look at all of this from the perspective of systems level understanding. And that's what I've been working on, and I hope that that's something which feels comfortable to everybody in this room. It strikes me as the best way of getting the right answers. Instead of having local answers that could be wrong, you get system-wide answers which by definition will be right. And one way to do that in the human brain, of course, is pictures. That's kind of how we think. So as usual, we're going to start the day with pictures with two friends from the Ski Institute. And I think you'll see this theme run through the day. When we get to the CTO Challenge, we're going to ask those wonderful people to do something which has never been done before. So part of the High Wire Act today is we've now spent some time building up the layers of a compute idea from scratch. And we're going to ask them to do, I think, the hardest thing that we have ever asked a CTO Challenge to do. And it will have to do with some of the things we'll talk about first with the folks from Ski. And throughout the morning, I've tried to bring in people who are expert at things which will help inform this vision of a new way, a new theory, a new paradigm in how to compute at a very high level. And if it works, I think it will work, we'll leave here this week with a completion of all of this multi-year effort and with an understanding of the future of computing, which is much more exciting than before this week started. It's not hard to guess that at a time when all the chips are called brain-inspired, we should look to nature or to biology or that kind of thing for understanding engineering principles that might help get us to this place. And there's no better place, I think, to start than Ski Institute. And I have asked my two friends here to talk about, now so you've heard Chris Johnson lead off 3 or 4 years. He's now our FiRe leadoff player. It's kind of a baseball team. He's our lead hitter. And it's a wonderful way to start the day, but it's also so informative because the visualizations that Chris and his team have done are beautiful and informative and help us see these very complicated things. Last year, as he'll talk to us about, it was float interaction, and this year it's something completely new. And you'll hear the term pictorial processing thrown around today. And that's the layman's term for what could be a much more complicated thing in n dimensions. But basically, it has to do with using our brains the way they work and creating a brand new way of computing. I want to mention before we start that, because I don't think Chris will tell you this, Ski Institute, I think by 2 different objective groups, was named the world's most important visualization institute this year. So congratulations, Valerio. Congratulations, Chris. Yeah. Very cool thing. So we picked the right horse, it turns out. Chris, would you like to start off?
I would.
Okay.
Thanks, Mark, and good morning, everybody. Last year, can you put my slides up? Thank you. Last year, if you were here, we talked about flow and visualizing flow, and the flow could be from fluids, it could be the flow of electricity within our brains, and this year we're going to connect that flow with ways to visualize visualizations, and how can we think about doing analysis through visual processing. And there's a couple of images on my slide that we'll explain a little bit later, a little bit of foreshadowing. That bottom left image is the highest resolution mosaic electron microscopy image of the retina of our brain, and Dr. Brian Jones is going to tell you more about that, which is, we've worked with him, it's very exciting. The one right next to it at the bottom is one time incident in a very large scale combustion simulation where you'll see the flame in a volume rendering, but you also see these dots connected over there, and that happens to be a topological analysis of the ignition and extinction events, and we'll tell you a little bit more about that. But first I want to put this a little bit into context and a little bit of history. Since I'm a professor, we do that every once in a while. Anybody know who this person is? I'll give you a hint. He invented the fast Fourier transform. Does that help? How about here? Here you can see him more in his day of the computing. Close, but not quite. It's John Tukey. And Tukey invented something called exploratory data analysis. This is back in the late 70s, early 80s. And what he was all about was finding ways to use visualization to do the analysis. He invented the box plot, which is the most used visual representation in statistics. One of my graduate students, former graduate students, Christy Potter, actually generalized that to do some summary statistics, but that's a different story. Here's some quotes from John. You know, the greatest value of a picture is when it forces us to notice what we never expected to see. Exploratory data analysis isolates patterns and features in data and reveals them forcefully, I like that, forcefully, to the analysis. People can recognize patterns not captured by data analysis tools. So he was all about this transformation of what was before was entirely non-visual. It was all about the statistics and the numbers. And John Tukey was the one that took us to this exploratory data analysis using visualization. So that got us to box plots and looking at things on two-dimensional analysis. What happens when we have much higher dimensions? This is a problem that scientists and engineers face every day when they're doing analysis of very high dimensional physical or biological or other phenomena. So this is a 10-dimensional combustion simulation, and the way that they do this is traditionally, if you see that right, those sets of two-dimensional plots. So no one can reason in 10 dimensions, at least I haven't met them. We're good at 2 dimensions. Some of us are pretty good at 3 dimensions. Once we get beyond 3 dimensions though, 4 dimensions, 5 dimensions, we don't really have that capacity to easily understand this. And so what is typically done is we'll take those dimensions and we'll break them up into all the features, dimension 1 against time, dimension 2 against time, dimension 3 against time. And then the scientists will take like pairs of those 2D plots and watch them over time and try to create a mental image of what's going on in their brains. And that's proved to be at least somewhat successful, but it's difficult. And so one of the challenges that we have is there a better way that we can represent those 10 dimensions visually for us to understand and analyze? And what you see in the middle of that is an abstraction, a 3D abstraction that captures all 10 dimensions over time of that combustion simulation. And this is work by my colleague here, Valerio Pascucci, and another colleague, Ross Whitaker, who has been up here previously. And this enabled the scientists to actually discover new phenomena that they had not seen before. They had stared at those 10 2D plots for decades. And by making this into a 3-dimensional new abstraction, visual abstraction that captured all of those 10 dimensions, they were actually able to realize some new things that they had not seen before. And so this idea of can we come up with new abstractions, better ways for us to capture and understand that data, that high dimensional, often large scale data, is one of the challenges that we have. And to take you there and give you a sense of where we're going, I'm passing my baton off to Professor Valerio Pascucci.
Yeah, so this going to the specific theme of visualizing visualizations is actually looking at a 5-dimensional space, but on the right you see the animation of the space itself. You just start seeing rotation and exploration. On the left actually is visualizing the space of visualization. So you can see, for example, for that structure, there are the blue areas, 3 important visualization that reveal more information. So interesting, actually, the space of visualization is much larger than the space of the object itself. And so it's very important to understand formally and systematically what possible things you could be seeing when you explore a data set and what mental pictures you can create. And so with this line of work, we kind of look at high-dimensional data set, and instead of making a person spend a long time to build a mental picture, we start building visualization that are very close to that mental picture that build a human intuition. So for things like this, we use systematically tools like, oops.
Press, there you go. There you go.
Like topology, statistics, and so on, also to make sure that the results of the visualization are not biased by the expectation of the user. That's a very important component in the scientific discovery. So this is, for example, a case of what they call the Karman Vortex trick. So it's a sequence of vortices that creates, for example, when there is wind, say, going around an island, and those are the clouds around it. So, and when a scientist studies something like this at the end is the diagram that you see at the bottom is really the mental summary. They don't want to have all the details. They show some of those lines and the direction of rotation and so on. And a major challenge is to use integrated visualization and analytics to actually automatically build up abstraction instead of waiting years and years for individual, very smart people to do it. And so we're looking at doing this also for time-dependent data as well. So the type of work we do is, for example, taking the flow of this particular type of data, this vortex street. We can subtract some of the monotonic, kind of the boring, non-informative part to it. And then with the topology, we can start segmenting automatically in regions that actually are structurally similar to what scientists took a long time to divide and segment. And then looking at rotation and so on, so that we can build a symbolic model, a mental picture, very close to what a scientist would do, but this in a fully automated way, so without waiting a long time for people to do that summarization. And so this, we're building tools for doing something like this. So this is a case
So Valerio,
yes.
quick question. That was discovery.
Yes. So this is a new process.
When you say instead of waiting for a long time for some guy to show up or woman to show up to do it,
Yes.
that's discovery.
Yes.
Yeah.
And that's the idea. You want to, I mean, as Tuki was saying, so you want to highlight something new that you did not expect.
Yes.
And so in many of those visualizations, in fact, in all of those that we show, typically there is one aspect that the scientists saw for the first time. And typically the question is, how long would it take for you to see it? And normally the answer is like, well, probably I would never be able to just see it.
So by doing the visualization of the visualization and then abstracting it even further, you make a discovery,
Yes.
which is made at this very high level of abstraction.
Yes,
And yet it's a very true discovery. It's a real thing.
that's right.
Yeah, okay.
So then you give the insight. Obviously, people go back and double check, validate, and so on. But you give the key insight of, is this fact true? In fact, you help developing the questions that they have to ask. That's
Okay,
how.
I think we're done.
Okay, that's good. We're early.
No, I mean, that's beautiful. That's exactly what we're talking about. Okay, I'm sorry, go ahead.
And so, the question is how systematically you can do it, right? So we see this all in science, done in many ways, in a very specialized way. And our interest is, as a computer scientist, using a lot of these mathematic techniques, can we do this in a fairly systematic way so they can apply across disciplines? And this is the type of things we try to do, is that here, say, on the right, you see this more traditional way of looking at combustion, lots of details and so on, and it's inspiring. But if you look at when it transitioned to the left, those are actual features that are in the combustion, and that's actually closer to what a combustion scientist think about it. All the pieces of extinction, reignition that evolve and how they move over time, that's really what creates the science. And can we systematically do those segmentation and evolution? So for doing this in a general way, we are looking at trying to develop a kind of a visual alphabet, you will, a visual language. So the small picture that you see on the top and on the left, those are in the letters in the alphabet in this language of topological representation and feature extraction. And there you see a data set. This is a CH4 molecule that instead of having to explore for a long time, the space is already divided in regions where things are monotonic, things are moving quickly. So I know very quickly, very precisely, that's the most important part, what's going on.
This is methane.
Yes, this is methane. And so suddenly I don't have to explore a lot, I don't have to know a lot in advance. I know the structure of that field, and it's completely unbiased because this is a purely mathematical language. There is no expectation of the user to want to see something. That's one of the danger of big data. If you really want to find something, you will find it, whether it's there or not. And so with this type of language, for example, we try to look at across multiple type of science applications. This is, for example, the analysis of a porous medium. Is actually what happened in Lawrence Livermore National Lab, where they're doing the fusion experiment with lasers on a tiny target.
Ignition?
So with the National Ignition Facility. And so they're firing those lasers and trying to implode this type of material. And that's why they do this very detailed analysis. They want to know the porosity of this material and how that evolves over time. And you can see that here, you start, say, with terabytes of data. We extract the feature and the structure of the data, so it gets way smaller and more precise and informative, closer to what, if you think about that graph, is what you think about a porous medium, not all the single molecules and so on. So we eliminate the details that become distracting and get you to the science part. And then you can measure strength, you can do all kinds of things, but also you can compare two materials and say, oh, yeah, are they similar? Are they structurally? What is the failure? You can ask a bunch of scientific questions and reveal precise answer this way. This is an application that actually we're focusing on right now, brain of primates. This is actually for macaques, and we're working on exploring the brain, the brain initiative, the massive amount of data. We're using all kinds of tools, including virtual reality, so that people are fully embedded in this pictorial way of walking through the brain. Yeah, you saw it. It's anybody that visits Key, I invite you to go through our demo. That's really fun to do.
Yeah, so I did this a few weeks ago, and this exact thing. And so you put on your VR goggles, and you can see before it's traced, because this is being traced by a person or by grad students. That's what grad students are for, I guess.
I'm very good at it.
Yeah, and you'll see in 3 dimensions this very complicated nerve structure, which is nothing like brain-inspired chips today. Yeah. It's very complicated. There's a lot going on there, and you can see the whole thing pretty much. Mm-hmm. And you walk around inside of this nerve structure. It's like, wow, you're inside the brain. Yeah, that's an amazing experience.
Yeah, it's very cool.
And you quickly get the picture.
Yes.
I mean, I don't know how else to say it, right? You know the structure, how it evolves, and it's more accurate. And it's much faster. I mean, people sometimes spend years doing all the segmentation, and we've shown that the quality is improved, and you can save years of people time just to do the segmentation and have precise answers out of that. So, and this to show kind of different areas. Here, is the design of an ion lithium battery. So there is a lot of work in national labs everywhere to design new battery. Everybody would love to have their phone last at least twice as long. And so here, it's large-scale simulations, and you see here overlaying the structural features computed systematically on a computer at a certain scale versus the volume rendering on the data. And you see how you can focus in this case, for example, it's important that the cycles in that network, if they have 6 sides, then your charges are well contained and your battery will last long. You can quickly find defects when they have 7 sides, 8 sides. The material is not perfect, your battery will not last that long. And then they can design a new material, but more important, they can understand why those defects are formed. You answer those important questions and develop a new process or a more pure material to get into a new discovery, something that has real impact in people's life. And so talking about abstracting how people think about also, those were more static examples, but most of the time people think about trends over time. And so what we do, in addition to computing scales and features in the data, we compute trends. So here...
Would you call those flows?
Yes, actually, this would fit also in a generalized notion of flow, so how things evolve over time. Yeah. And so the graph here on the right is the flow in a more abstract way. You look at a flow as a sequence of events, when things merge, where things are split, when they're born, when they die, in a time evolution. So the horizontal axis is time, the vertical axis are the elements in your particular scientific study. And I'm being generic because we are building tools that are generic, and I'll show a few examples quickly. And so then the graph, so if it has just a bunch of horizontal lines, means, a bunch of things are independent and just go on. The more they start split and merge and so on, the more the complexity of this model is created, the more you have a phenomenon that requires attention, where things are related to each other. You cannot study them independently.
Could you kind of say that the better, I don't know what you want to say, understand or comprehend, the better the treatment is at understanding or comprehending that system, the more condensed the visualization is?
That's exactly right. Okay. So the more you know the detail, the more you, in some sense, can eliminate and simplify and go to the next level. Mm-hmm. So each of those stages really are based on validating the lower one, the lower in the level of abstraction, but then has more data and more detail.
I'd like to ask you a meta question.
Yes.
So I remember a time when I was first studying algebra and math, and a lot of charts and a lot of science charts. And you got to the point where you could just kind of look at the chart, and you kind of knew. You kind of knew, like, what was going on, whether it was acceleration, whatever it was you're looking at. Parabolic, whatever was happening, you'd say, I get that. You could start thinking in terms of charts.
Yes.
Do you get to you're way beyond this. Do you get to the point where you can just take a quick look at all this stuff and go, I get it. It's too complicated. Hasn't been resolved yet. I see the 5 patterns that are inside that information. Are you at that stage where you're looking?
Yes, and in fact, actually, we are actually at the next level that we see when we look at one of those charts, we can also tell whether there is noise in the chart that requires recomputation. So, for example, there's a lot of phenomena that here you pick thresholds, define features. You look at the charts, you realize, my definition of the features was slightly incorrect. Yeah. Then I adjust that, and now my chart looks simpler. And so you know that that's a good indicator that you have improved your definition of the element that you were studying. Yeah. So there is a cycle into that really brings new knowledge. It's not just showing something.
And when Chris was talking last year about flows, you were really strong on interacting with the system and reiterating just the way I think you're talking about it now, Valerio.
Absolutely.
And
yes.
Where I'm driving with this is, from your intuitive understanding on that level, is there then a language that one could create that would replicate that
yes.
comprehension that you have?
That's absolute. That's where we're in a way, struggling, but that's really where we're focusing on. There has to be an intuitive, generic language. In a way, we've seen in science, like every science has its own language to become very compact in the way they describe structures and features, like a name of a chemical species and so on. Here, we're really shooting for a common, compact language for describing those features.
Cool.
And so, yeah, so for example, this is the time evolution of some of the combustion example that I was showing before. Now, the same class of tools you can use to look at the evolution of discussion groups in social media. So the fact that you are describing groups kind of as a generalized notion of clustering, it could be a feature in combustion simulation, it could be a group of people, and then you still, here is in the middle, look at the evolution of how discussion groups merge, split, are born, and kind of die out. So there are patterns that go beyond the specific application, and they are the way we think about time evolution and features in the data.
So when the Russians show up,
oh yes, the blue dot. But you want to also, as you were saying, go back and forth, right? You want to look at, each of those dots, then I go back and look at the words involved in that discussion, because I have to drill down back and go back to the abstraction and validate the results. Here is looking at evolution of people entering the healthcare system. So we look at data from the veteran hospital and looking at how they would enter, how the conditions were annotated, and how their situation evolved over time. And again, you have a pattern of people going in, out, and so on. And here is studying climate and weather. Those are like region in the ocean. They have a certain mass and they move and bring matter, energy, and so on. Are again features in your data, and they evolve over time, and they may or may not interact. And that's extremely important to understand if you want to understand how climate evolved and how weather evolved. And this is the last one, is kind of in plasma surface interaction. This is for fusion application. This is for development of new energy sources. Again, you want to look at how those evolve over time. And that complex graph, unfortunately, is not yet good news, is that shows how the current state is in some of the simulation of what would happen under those fusion conditions. And the scientist knows that until that graph is simplified enough, so there are not too many interaction with the surface boundary, they cannot have a stable fusion condition.
I can just look at that thing and say, well, we're not done yet.
Exactly. So, and that's where, I mean, it's very important. It's a way for people to understand, and it's a way for people to communicate with other scientists, with other people. So it has validity at different level, and they can even show it to us so we understand. So we don't need anymore to study everything to understand some of the core value in the science they're doing.
And listening to what you've just said, I feel as though you brought the idea of flow and interaction into these visualizations.
Yes.
One last question, then we'll have 5 minutes for questions from the audience. We have places to stand. If you want to ask a question, we have 2 microphones here. You can get in line.
You want to go back?
No, it's okay. In our very first part of this conversation, you're talking about visualizing the visualization and then creating an abstraction of that. Is that where pattern recognition occurs?
Yes, that's what, in a way, visualization implicitly has pattern recognition. That's what we're extremely good at as a brain machine.
Yeah.
And that's the power of, if you build this visual representation, 2D, 3D, or even high dimensional, with the proper training, now suddenly the pattern recognition goes in kind of wild and find all kind of things that we couldn't find before.
Right.
So, absolutely. Yeah.
Perfect. Okay, this is really cool. Questions? Do we have any questions? If so, they're all stunned. I think they're still having their coffee. No questions at all. I'll just keep asking questions if you guys don't have any. Okay, so in this language, where are you in the evolution of this language? And if you do have a question, yell or something. So in this language thing, where are you in the evolution of this language?
So I would say it's the early stages, but enough to actually have very interesting results. So for example, what I had in that image, let me try to get there. Yeah, here, for example, we have some of the key character in that language. So here, this is particularly focused on topology. And here you can see that the dots are the extrema, so the places where the flow starts or changes direction and so on. There are some key planes where that's separated. There are key lines. Those would be lines along eigenvectors of those critical points. But those are important lines where the flow has a changing behavior and a structural that you really want to look at that area and not the rest. And I think that's the important part. The visual language drive your attention, since you have to deal with a massive amount of data, drive your attention to the places where really the action is. Now, the completeness of this language is what we're not at. So we need to do much more for this. But the power is that can be embedded in the visualization itself.
Yeah.
So that's a big advantage of what we have now.
And having this language, whenever it's completed, you can imagine doing computation at this level, can't you?
Yes. So then I can do my analysis, my processing, and that's where actually the comparative, the pictorial computing, I think, will come, because if I start comparing pixels, it takes a long time, and there is a lot of noise, and it's very hard to make sense out of it. But when I start computing over those surfaces, graphs, or even higher level abstraction, now you really do something much more similar to what the brain is doing. And so you can really make similarity, understand what the structure does, what is the function, and so on. So that's what we're shooting for.
Mark, I have a question.
Yeah. Louis.
Yeah. I saw your application to social media.
Yes.
I was wondering if you have ever tried to apply it to a more homogeneous population of users, say in the agricultural market, where there is great sets of discrepancies about adopting technology for various reasons. Same thing with what Dr. Hood was talking about last night in the hospital environment and in the medical system environment. Have you ever tried to look at homogeneous populations who are, predominantly the same type of users, like farmers, and their supply chain?
So,
Thank you.
so the idea is great, but the key word is try. So the problem is with a lot of those direction is really finding a good data set. And that's actually what we haven't found quite yet, a good data set that we can try in that direction, that we can try the technique out. That's why, so Twitter was an easy source because it's out there and we can take it. So to do more systematic testing in much more control environment, introduces the challenge of collecting the data. So yeah, we would like to, but we haven't done it. So
He probably has one.
Okay, then I'll be interested in you.
Go ahead.
I just had two quick questions. One, did Edward Tufte influence y'all at all, or?
Oh, of course. Edward Tufte is, he was one of the people who took some of John Tukey's exploratory data analysis and took it to the next level. Yeah. And the Tufte books are well worn on our shelves, absolutely. Yes.
I had the pleasure of attending one of his seminars. But my main question is, the holy grail in diagnostic ultrasound imaging is tissue characterization. And for the last 30 years, everyone schleps out to a conference back east and says, we're really close, next year we're really going to get it. So are you guys looking at all in terms of medical imaging and computer-assisted diagnosis, or be able to visualize?
We are. We have a whole team of people that work on image analysis of different types of images. We haven't worked so much in ultrasound, more in magnetic resonance imaging and CT scanning.
Well, that's easy. Ultrasound is hard.
We have done some in ultrasound, and it is hard because it's noisy. And yes, but these kinds of feature extraction types of techniques might be applicable to things in ultrasound. We haven't tried it though.
We'll stay in touch. Thank you.
Yeah, we'd love to
I'm
get
afraid
data.
we're out of time. Sorry. Thank you both. I think you just did a marvelous job of starting our
Great. Well,
path.
thanks.
Thank you very much.
Yes, thank
Thanks
you.
a lot. Thanks, Valerio. That was great. Really cool.
Anybody with data, we would love to have it.